It's time to put everything we have learned into practice. To truly understand the power and the limitations of near-intermediate scale quantum devices, you need to see how different algorithms handle the same problem. In this milestone project, we are tackling a classic in combinatorial optimization, the weighted max cut problem. But we are not just using one method. We are going to conduct a comparative analysis between two of the most popular variational algorithms, QAOA and VQE. By the end of this project, you have moved beyond simple hello world programs. You will be optimizing circuits using Qiskit's latest primitives, V2, simulating noise, and finally sending your optimized parameters to a real IBM quantum computer. Here's your challenge. We have a graph with 5 nodes and 7 weighted edges. Your goal is to partition these nodes into 2 groups, set A and set B, such that the total weight of the edges connecting the 2 sets is as high as possible. With only 5 nodes, there are 32 possible ways to cut this graph. This is small enough that we can find the ground truth classically, which will be your first task. To complete this project, you will need to follow a rigorous 3-part workflow. Part A is your classical baseline. You will write a brute force script to find the exact maximum cut value. This is the perfect score our quantum algorithms will aim for. Part B is the quantum implementation. You will map the problem to an Ising Hamiltonian using poly-Z operators. You implement QAOA at depth p equal to 1 using the sampler V2. Then you implement VQE using the hardware-efficient ansatz like TwoLocal and the estimator V2 primitive. Part C is the analysis. You will run your optimizations on the Aer Simulator first. Once you find the optimal angles, your gamma and beta for QAOA and your theta values for VQE, you verify them on a real IBM quantum system. How do we know if we succeeded? We are looking for an approximation ratio of 0.95 or higher on the simulator. We will also compare the probability distributions. Does QAOA give us a sharper peak for the correct answer than VQE? And how much of that accuracy do we lose when we move from a simulator to a real noisy hardware? Now, here's the challenge to you. Try to solve this on your own first. I have provided a PDF with the problem details. Use the Qiskit 2.0 documentation, look at the primitives V2 syntax and see how far you can get. Don't worry if you get stuck. That's part of learning process. In the very next lesson, we are going to open up a Jupyter notebook and code through the entire solution together, step by step, from the first import to the final hardware job retrieval. Can you beat the classical baseline with the quantum circuit? Let's find out. I will see you in the next lesson.